Nice. Okay, here we go. Ugh. All right. Okay, so here's the next thing you write. Boom. What did I just say? Input, output. So we're doing parabolas and just basic quadratics and what they look like. Same thing. Quadratic is an x squared, which graphs to be what's called a parabola. 0 squared is 0, 1 squared is 1, 2 squared is 4, input, output. -1 squared is 1, -2 squared is 4. Say hello to the parent quadratic. Anything that we talk about from here on out is based off of the parent, where the vertex is at 0, 0. I do want you to write this down. Axis of symmetry is x equals 0. And you know, people have a lot of problems with this, remembering this. This is a line. That is an equation of a line, and that's an equation of a vertical line. So do make sure you understand that. That's why we say the axis of symmetry is x equals, and it's x equals 0, which ends up being the y-axis. Why it's called the axis of symmetry is you have points that are symmetric about that line, flashed across that line. And that's true for the whole parabola going forever up. Okay? So down there, the axis of symmetry intersects the vertex and divides the parabola in half. Everyone good so far? Thumbs up. Pretty simple stuff. Have you seen this before? How many people have seen this before and know what they're doing? Okay. All right, so we're really going to break this down slowly. You feel free to, write what you want. Like I said, be professional. Do what you need to do, you think, to understand. 0 squared, and then this is weird. They go by 0.25s. 1 squared is 1. So here is the parent function. Now we're going to make some changes. -1 squared is 1. Here's the parent function. So what are these green and blue functions? How are they different? Well, what happens when I put a 0.5 and then square it? Did I just do green there? I did. I went blue. Well, it's a simple order of operation thing. When I plug in 1, I get 1 squared, which is 1. But then I multiply by 0.5 and I get 0.5. Whoa, this graph changed. They use the term wider. I don't like that. What this is a vertical. There's two words we can use on this. It's a vertical shrink or compress. And I'm going to put the rule on it right now. I'm in the way over here. Can I move this? Vertical shrink or compress. My face over here is bothering me. And this happens when this is when we're putting a in front of x squared. What's the change? When a is between 0 and 1. We're going to talk about when it's negative. That's something different. That's not a shrink or compress. Okay, so he said, how do you know that the orange is the parent? First of all, it's red. Sorry, it may look orange, but it's because look at here's 1 and here's -1 and here's 1. So 1 squared is 1. Okay, input output 1 comma 1. So that is the parent function. F of x equals 1x squared. No, I think I'm going to keep my face there. Ryan, is he saying something about my face? All right. And then green, f of x equals 2x squared. I know I was complaining my face was in the way of the writing. Gotcha. Okay, 1 squared is 1, but then you multiply it by 2. So now we got that green function. -1 squared is 1, but then we multiply that by 2, and now we get this picture. This is a vertical stretch. And what are we talking about? We're talking about compared to the parent function. So this is vertically stretched compared to the red y equals x squared function. And this happens when a is greater than 1. You'll get stretches by whatever that factor is. And that's how you word it. The green one is a vertical stretch by a factor of 2. The Blue one is a vertical shrink or a vertical compression by a factor of 0.5. Is everyone okay so far? All right, so good question. Hopefully, Adrian, I got that good for you there. The coordinate plane's a little weird. They go by 0.25s, so it might have been hard to track that, a little bit. But they had to do that so that we could see that 0.5x squared a little bit better, I'm sure. Okay. Everyone all right? I'm going to just tape this whole thing and then see what happens. Hey, I wore my math team shirt today. Okay. How does a sine affect a of x squared? Let's just take this down. Signage. Right, so I'll just move to that and just show you actually the very good math term. When a is negative, you don't think of stretches or compressions. It's a vertical reflection over the x-axis, or just say reflection over the x-axis. So a reflection over the x-axis is the term that you want to use on this. Very simple to do. I always like plugging in 1. 0 squared is still 0. 0 times 0.5. This is not the parent, right? That's a vertical stretch of 1.5, just a little bit. 1 squared is 1, but 1 times 1.5 is 1.5. So it got pushed up a little bit, -1. So there's this graph. How does it compare to this graph? Well, when I plug in 1, I square it, but then I multiply it by -1.5. Still have 0, 0, because 0 times 1.5 negative is still 0. And -1 plugged in gives me the same value here. So there you see this graph is going upside down. Sometimes they use the term flipped. So be careful on the books. Like Wednesday, I'm going to have a little book thing like I like. This is a checkpoint for everyone that should get 100 because you get the infinite number of tries on those questions I give you, blah, 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 blah. All right. But then there's the general rule. If a is greater than 0, the parabola does open upward. If a is less than 0, it opens downwards. We do like to call that a reflection over the x-axis, though. So go ahead and take a minute to take that down. Any questions, feel free to fire away on the mic. Well, wait, is this a class I can't hear? Peyton, can you just say something? Turn on your mic. I want to see if it turned back on. Unbelievable. I don't know what's going on. I don't know if I hit something. I can't hear anything. And then there's your chance. You could have been on the video. But no. Huh. That's weird. Everyone else heard, Peyton? Wow. Maybe I did something. You know what? Maybe I hit a button. Oh, Peyton, turn it back on. Did you say something? Yeah. Thought I hit something here. All right, we'll move on. Okay, now I threw something at people last hour and I kind of made a mistake. Function values are increasing and decreasing. I actually do want to graph this too right above my face here. Oh, it's a little shaky there. Okay, so they picked 4x squared. You'd say that's a vertical stretch by a factor of 4. But let's just look at this very easy input. -2 squared is 4. 4 times 4 is 16. -1, -2. Let's go 4, 8, 12, 16. Let's go by 4s. So -2 comma 16. -1 squared is 1. 1 times 4 is 4. 0 squared is 0 times 4 is still 0. And then symmetry. Symmetry. Now, I'm going to throw something at you that I accidentally threw at second hour because I'm going to keep you equal. Don't worry about this for right now. It's a nice little added thing to know. But this is legally, mathematically speaking, how you're supposed to name how the intervals in which things are increasing or decreasing. So it says over what interval is f of x increasing, and over what interval is it decreasing. Now, a couple people last hour told me they have seen interval notation. I'm going to do a real quick explanation of interval notation using a number line. Here's a number line. Here's 1. Here's an open dot. And here is a graph of that. How many people have seen a graph like this before? Just a number line graph. And all this is it's the same thing as x is greater than 1. That's what that means. Here's how you write this in interval notation. What is that answer in interval notation? So it starts at 1 and it goes off to the number that's way off to the right on the number line, which is called infinity. And what I need on that 1 is a parenthesis. Parentheses are synonymous with open dots, meaning not included. How many people have seen this before? Interval notation, raise your hand. Okay, so there we go. We got a problem. Some have and some have not. Let's throw another one up here. And now you have all seen it. Let's just say -2. Let's fill in that dot. And let's go this way. Blah, 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 blah. Everyone knows that that is x is less than or equal to -2. Okay, less than or equal to. For interval notation, you must go in order. You must go in order from what is this number all the way over here and name interval notation from left to right. And the answer is -infinity is way over there, all the way up to -2, and then it's a bracket. Brackets mean included, means equal to as well. Okay, how many people have seen that? Know the bracket thing. All right, it should be all of you if you were in Math 1 honors, I would hope, but maybe those that didn't raise their hand, they just forgot, let's see. Because here's what you got to do when you're naming when things are increasing and decreasing. You must go in order from left to right. That's how you read a graph. So I must plug in my x values from left to right, and then notice these y values from left to right. They are going down. Or when you look and I plug these x values from left to right, these y values are going down. So you can see it in a picture as well. So this graph is decreasing. Now here's the kicker. Just put DEC, decreasing. You need, the word decreasing is already describing the y's. The interval that it decreases in is the x's that you plug in from left to right. So what do I have to plug in for left to right to get these y values to decrease? And the answer is from -infinity all the way up to 0 for an x coordinate. Always in increasing and decreasing intervals, it's just parentheses. Because the idea is I really shouldn't include this 0, because at 0, there's a change of direction. There's something unique happening there when we do that little move there. Then increasing, well, when I plug in 0, then 1, then 2, then 3, then 4, I get 0, 4, 16, and then these start taking off crazily. I could see it in the graph as well, that once I plug in these values in order from left to right, the y values go crazy forever, increasingly going up. I said that weird, but anyway, 0 to infinity is where the graph increases. So a real quick reminder of interval notation. It's the only way I could tell you what interval these are increasing. So these are the x's that you plug in. That's the specific name you need to use for that, or specific notation. Y's are already being described by the increasing, decreasing. So, all right. Okay, so I pulled this out of your workbook. Don't bother grabbing it out. I just wanted you to know how the 3-1 assignment's actually really basic and simple. These are most of the questions. How does the value of a in each function affect the graph when compared to the parent? All you would say is that this is a vertical stretch by a factor of 4. I'm just going to put by 4. Okay, and you can expect it to be skinnier, but I don't like using that term. It's not a mathy term. When things are vertically stretched, they're not always skinnier. That's the problem. These affect all functions the same way when you have some sort of multiplier like that. So it's just not a good math term. I'm going to skip to this one. This is reflected over the x-axis. That's what I want to say. Don't say down. When you get into book stuff like what I'm going to assign you Wednesday, they might have multiple choice that say down. It goes down now instead of up. I like the reflected over, excuse me, the x-axis. And then vertical shrink by a factor of 0.4. You ignore the negative on the shrinking. We already took care of the negative with the reflection. Okay? Very simple assignment, just understanding that stuff. We'll get into something more complicated. Yeah, that's not certainly one of them. And then I just wanted you to be able to read a table correctly and actually analyze that equation with this increasing and decreasing stuff. Oh, okay. Doing good, doing well. Okay, so just giving you a chance to write this down. Maybe don't write it all. I mean, I don't think you have to write this. Hopefully you understand that this is x comma y. That's the x comma y table. And we shouldn't really be having to write, what did I do? Not really having to write this last table down. Because that is, those are the coordinates. Okay? So speed you up there. Then notice, do we notice though, as I plug in these x's, what are these y's actually doing? Well, should really focus on that. What would you rather owe? Would you rather owe $1.20, owe 30 cents, or would you rather owe $0? What would people probably say? I'd rather owe. Thanks, Jad. I saw the big zero up there. All right. So that proves that these are going down. You got to think negatives correctly. Or maybe quick snap graph this 0, 0, -1, -0.3. I'm sorry, going up. Did I say down? Oh, no, I made a mistake again. These are going up because they're increasing in value. Then here's -1.2. If this is -1, here's -1.2. This graph looks like this. Whoa. Right? It's an upside downer. So when I plug in x from left to right, this goes up, then it goes down after this. We could see these going down. 0, when I plug in 0, 1, and 2, these go down in value. 0, then -0.3, then -1.2, so that decreases. Okay, so this one, interval notation again, increases from -infinity to 0, decreases from 0 to infinity. Little flippage there because these are flipped upside down. Okay, sorry for that mistake. And when I said decreasing, when I meant increasing. So seeing it in the picture can also help out. And then this is a stupid little question. I gave you 23 and I panicked. Oh, will they not know what to do with a triangle? Boy, I hope you know an area of a triangle. But this is a square, telling you what's in your homework. So, okay, write a quadratic for the area of each figure. Well, this is just a square. Area of a square is side times side, or side squared, or length times width. I don't care how you approach it. That's the area of that square. Oh, this is ridiculous. Why don't I even give this as an example? Too easy. Then if you were to label this, it'd be units squared. Okay? So you have a triangle. They ask you to do that, and then some other stuff. So 3-1's pretty simple. Did want to teach it like it's brand new. We had interval notation. Probably needed a review on that. So that's good. Stalling before we go to the next part in 3, 2, 1. Cut my head off too. There we go. Do you notice I got a haircut? Anyway, I cut my own hair. Save money. Probably some spots that I have to fix later. Okay. All right, ready? Boom shakalakas. Okay, so now this is what we're going to look at. Ooh, it looks a little blurry. There we go. Kicked in. Now we're going to start changing some stuff and then use this in terms of how functions get affected as well. So for parabolas, we're really going to focus on the vertex, but we're also going to talk about transformations as well. It's very simple. Input, output. Anything that we graph this year, I hope we have the time to just input, output first, so that you understand that basic concept. There's the parent. 0 squared is 0. 1 squared is 1. 2 squared is 4. Negative 1 squared is 1. Negative 2 squared is 4. And so on and so on and so forth. Don't get yourself a real fancy coordinate plane here. I just did this for no purposes. Just do the quick, okay, for all three of these. And then, we can analyze h of x. This is why I like function notation. 2, you can name things a whole bunch of different names. F of x, h of x, j of x. All right. Right off the bat, when I plug in 0, I get 0 squared is 0 plus 3. 1 squared is 1 plus 3. Oh, I see. 2 squared is 4 plus 3. Oh, I lost my 1, 2, 3, 4, 5, 6, 7. Because negative 2 squared is 4 plus 3 is... Are you okay, Emily Ann? Rubbing your eyes there. Is the math hurting you? All right. Scared you. And then the other one, j of x. Oh, this is Mickey Mouse stuff for some of you. 1 squared, 1 squared, or 0 squared is 0 minus 2. 1 squared is 1 minus 2. 2 squared is 4 minus 2. That's my reflection song. Okay. Oh, and I should talk about axis of symmetry when things are changed. All these axis of symmetries are still x equals 0. But how do these compare? I hope you simply see that moved the parent up 3. So how does it compare to the parent function? And this one is, I'm in the way again, down 2, right above my head there. All right. Sorry. And then we got this. And hopefully we can analyze this correctly when we look at these. Again, the parent, 0, 0, 1, 1, 2, 4. Feel free to not draw this again. Just trying to hammer down the point that we're comparing this to this. So that's what the terminology is. Wish I had a bigger coordinate plane so that it looked bigger, but that's all right. Okay, so h of x. Now it's x plus 1 squared. Watch what happens. I'm going to get right to it. And hopefully you just grab it and accept it in this e-learning experience. Get this concept fast. First thing I'm going to do, well, what happens when I plug in 0? 0 plus 1 is 1. 1 squared is 1. Weird. You know what I'm going to do? I'm going to plug in the number that makes this set of parentheses 0. Watch what happens throughout the whole rest of these notes when I do that. That number is, what is it in the chat? Come on, if you're just seeing if you're paying attention. We have, bam, Matthew, Ethan, nice. That was awesome. Negative 1 plus 1 is 0. 0 squared is, oh, whoops, that was a slip up there. Negative 1, 0. Okay. What happens when I plug in negative 2? Negative 2 plus 1 is negative 1, but then square it and I get 1. Aha. I've located the vertex by finding the number that makes that set of parentheses 0. Be careful. All right. We have a new form that we're going to teach Thursday that has some similarities there, but 1 plus 1 is 2. 2 squared is 4. Here's the 4 value. And then that means that should be negative 3. Negative 3 plus 1 is negative 2. 2 squared is 4. Nice. Try to get it to be nice and curved. That looked a little sharp. Hopefully you can see that this got moved left 1 compared to this. That's exactly what happened. And then, of course, for this last one, I don't want to have to rewrite it again. But look at what happens when you plug in 0. Oh, no. 0 minus 5 is -5. -5 squared is 25. It's like way up there, off the grid, all right, as they say. So I need to do something different. What did he say? Oh, plug in a number that makes the 0. That's probably going to be where the vertex is. 5. 1, 2, 3, 4, 5. Is someone going to put that in the chat? Too late. Yes, 5 gives me 5 minus 5, which is 0. 0 squared is 0. Then that means when I plug in 6 and 4, I should get that, that relationship of symmetry. So let's plug in 6 first. 6 minus 5 is 1. 1 squared is 1. Boom. 4 minus 5 is -1, but -1 squared is 1. 7 minus 5 is 2. 2 squared is 4. Now what I'm showing is the axis of symmetry. I think I'll write this on this one. The axis of symmetry happens to be moved to x equals 5. So this is proof that this got moved 5 right. That's the transformation. Brian, there's that sock symbol. I like it. What happened to your camera? Okay, so here's the kicker. And here's where we get this all synthesized. And feel free to not write all this stuff. I'm going to write it right underneath this. This is vertex form. And you need to have this memorized. There's going to be 2 other forms of quadratics that have different things that they give up, different attributes of the quadratic. They will all graph the same, except, there's going to be different approaches. Do put this in here. This is still a vertical stretch if A is greater than 1, a vertical shrink or compress. I'm going to use compress. I think one of the other math teachers in our group likes compress better. And I'm fine with it. I think they both work. If A is between 0 and 1, and it's a reflection over the x-axis, still, if A is negative. I'll say A less than 0. Okay? That's why we have these conditions for vertical compress and stretch. Negatives have nothing to do with the compressions or stretches. Okay? If A is less than 0, then it's reflected over the x-axis. Now, here's the kicker. H comma K is the vertex. I'm going to put that right above my head here. Vertex is H comma K. But I want you to put this in terms of, what does it do to regular functions, all functions, when we have this situation? And what this is H is a right-left shift. This is a right-left shift. Now it's weird. I'm going to put the words below it that you want to think opposite. Look at what happened up here. This goes against my brain, like what happens here. When you had x plus 1 on the inside of the parentheses squared, it went 1 left. When plus 1 feels like it should go right, positive is a right move. So I always tell my students, think opposite of what should happen there. But I'm also going to use that idea of plug in what makes that parentheses 0. And that's really the start of where the vertex is. And that should also take care of it. And then the k on the outside of the function is an up-down shift. And I always say that's the same. Look at 2 notes ago when it was, whoops, I went too far. Plus 3 was up 3. Minus 2 was 2 down. It's exactly what I would think they should be. And they are. So I always say opposite, same. Think of the opposite for H, think of the same for K. And that may help you, who knows. But actually, my approach to graphing is quite different. And I'll show you that with this particular situation. Okay, I'll give this a minute though. We do have the time, so Really, I should only have to do one more of these, but I'll show you a couple different approaches to it just to make sure we're all ready for it. And try to give all the transformations, or what they're called, on one of them. List, what would you list if you had to say what happened to this compared to the parents? Okay, here's the first one. Feel free to write these down real quick. This is from a picture. Can you come up with an equation? By the way, they started off easy. These are all 1 as an A value. So you don't have to worry about an A value. You will later in the last example. Okay, so giving you a second to analyze these. Sorry for the video, but I can't pause in this new thing that I'm using. It doesn't allow me to pause, so it makes me stop the video. So, alrighty. So we look at this first one as you're writing this down, and maybe not write all 3. I think it's a little overkill. Probably should kill the second one. Whatever. I don't think I'm going to cover that one. Okay, so 1 right, 2 down. So the vertex is 1 comma negative 2. What does that make the equation? Now, check yourself before you wreck yourself. This is just like good FOILers or good factors, right? Remember what I said. Well, maybe you forgot and you thought, okay, let me zoom in on this so I'm not writing so small. X, say you thought it was X plus 1. What? Plus 1 squared and then minus 2. Check this. Does that fit in this equation? That's what graphing is. Input, output. What's 1 plus 1? 2. What's 2 squared? 4. What's 4 minus 2? Not negative 2. I did something wrong. Oh, wait. Yeah, right. He told me to think opposite in here. This should be x minus 1 for a positive 1 right move. Let's check that now. 1 minus 1 is 0. 0 squared is 0 minus 2. Check, baby, 1, 2, 3. So even when you make that mistake, there's an escape out of it. All right. And then I'm just going to go to the right answer on the next one. The vertex is left 2, down 1. Check for scales sometimes. Sometimes they mess with their scales. They do go by ones. So negative 2, negative 1, right? Negative 2, negative 1. And then that means it's x plus 2, the opposite, minus 1, the same. Don't forget that squaring. Hey, let me check this. Negative 2 plus 2 is 0. Remember I told you about 0, the parentheses. 0 squared is 0, minus 1 is negative. Yes. So when I actually write that equation, my vertex fits in that equation. So therefore I know I'm at least partially right. Do you have a question, Patrick? Go ahead and turn on your mic. Oh, that's right. Your mic doesn't work for me. This stinks. Can you put it in the chat? What's John, Jad, and Adrian? What's with the carrot? Did I do something wrong? What? First problem should be what? Oh, negative 3. I got you. Oh, Emily Ann, you put it? Think it's supposed to be good? Yeah, okay. Gotcha. All right. Those are negative 3s. We good now? Thumbs up. I was just doing that to see if you were paying attention. Ha! Right? How many people believe me? Sebastian, no way. All right. I think I'm just going to do this one and skip these and then go to, yeah. So we're just going to go ahead and graph this. By the way, this is what I mean about this one as you're writing this down. And again, real quick coordinate plane, don't have to be fancy schmancy like mine. When you look at this, sometimes they ask, how is this different than the parent? I'm not going to write that down. So that's what these are. You have a reflection over the x-axis. So it's reflected over x-axis. This is compared to the parent. Vertical stretch by 2. 1 left, 5 up. That's how all the differences between the parent function and this one, all of the differences, all right? But here's how we're actually going to graph this. I think you should input output, and you don't put 1 in blindly. You try to find that vertex value. So I know that was the left-right shift. 1 right, 1 left. If it's 1 left, then what I should be able to do is plug in -1 there. So really what you want is start off with the vertex, prove that that's the vertex by plugging that in and then points around it on both sides to show that symmetry that I was showing you before. So -1 plus 1 is 0. Do your order of operations. 0 squared is 0. 0 times -2 is still 0. 0 plus 5 is 5. So yes, the vertex is -1, 1, 2, 3, 4, 5. Prove it. Plug in numbers right around it like 0 and -2. These are the next two numbers just to the left and right of -1. This is where you should see symmetry. 0 plus 1 is 1. 1 squared is 1. 1 times -2 is -2. -2 plus 5 is 3. So again, order of operations. 0 plus 1 is first, parentheses. 1 squared is second, exponents. Multiplication is third. 1 times -2, -2. -2 plus 5, add is last. All right, so the only way you could do that is if you do your order of operations correctly. -2 plus 1 is -1. Squared is 1, though. 1 times -2 plus 5 is also 3. There's proof. 0, 3, 1, 2, 3. And then we could do one more. It'd be 1 and -3. 1 plus 1 is 2. 2 squared is 4. 4 times -2 is -8. -8 plus 5 is -3. I don't know which one I plugged in there. I think I did 1. -3, 2 squared, -2 squared is 4. 4 times -2 is -8. Also -3. So next one, this is the skinnier aspect. Shouldn't use the word skinnier though. Vertically stretched. Okay, and then the axis of symmetry I'm going to put right up here. Axis of symmetry cuts it in half, and that happens to be at x equals -1, that vertical line that I have there. Okay, we're right at where we were the other hour, maybe with an extra minute. I'm not going to do those because it's just redundant. Notice what they say, find the vertex, axis of symmetry. I just found the axis of symmetry, that one. You really can't come up with too many more different examples of this. Really key on, if you're new with the vertex here, key on, plugging in the number that makes the 0 on the inside. That is where the vertex is located. And it gives you a starting point for your chart to make sure you do have a good sketch with a couple points drawn. Very, very smart to do so. Then I'm going to do this question to end. Wait, you just did a question like that. And I did it wrong the second hour. Someone caught me at the end. This has an added point. This is not like those ones where the leading A value was 1. This is a very common question. So here's a parabola, and I want to write the function in vertex form for this. Take a deep breath as we have a minute or so. But when it says vertex form, the next thing I'm going to write slowly is this. Okay, I want to write this. That's vertex form. By the way, you are going to have this memorized. There's 2 more forms you're going to memorize and what attributes they show. So you have to, and then be able to separate them. Okay, well, like that last one, this is the vertex. And I just found out that the vertex is these values. So I'm just going to go ahead and start off and do something, not nothing. I'm going to plug in that minus or -1, and now it's minus a negative. Then plug in plus this -3, I guess. I'm going to sit there and think, why did they give me this other coordinate? This is some arbitrary coordinate, like all these other coordinates are a bunch of arbitrary coordinates that represent that y and x. That's what that represents. That's the placeholder for the infinite amount of coordinates that make up the rest of the parabola. Well, they happen to give me this one. And that is, lo and behold, an x value. And this is, lo and behold, a y value. So I think what they're telling me to do is plug in the y, plug in the x, leave the vertex, and lo and behold, what I have all by its lonesome is a, and I can solve for a now. Booyah. So 0 plus 1, order of operations again. 1 squared is 1. 1 times a is 1a. Minus 3, negative 1. Silly thing, some people add these as like terms. Always see that on this kind of question. Redonkulous, don't do that. Add 3 to both sides. And then I have my a value, which is 2. So you bring the y back. You insert that new 2 you found. Yes, this is vertically stretched by a factor of 2. Now it makes sense. Bring the x back, but then the vertex is always the same for this parabola. Never changes for this particular parabola. So the vertex values come back, but these x's and y's come back for the other infinite amount of coordinates that make up this parabola. Now, before you leave, this word problem I was going to do, and maybe I'll do it Wednesday when we start. I have a word problem in your homework. This word problem is exactly like this question. I'm telling you, in secret, there are 2 coordinates in there that make me be able to do this work exactly that I did right here. So if you can handle that in a word problem, go for it. All right, I'm done. Sorry for keeping you.